All right. Well, good morning, good afternoon, everyone. Give me just a second here as we share my presentation. First, I'd like to thank both Barry and Bob for inviting me to participate in this. I think this is really an important topic, and it's something that, you know, Barry has given me a hard time about in the past, where we often talk about really advanced topics. Um, I recently made a presentation at an EPRI chemistry conference on a relatively advanced topic, but the topic assumed as a baseline that you had some common level of instrumentation installed, some baseline covered. But as Barry's data suggests, and certainly my personal experience, there's a wide number of plants that are under instrumented. They don't have the key measurements and the key locations to really keep their plant healthy and happy and operating successfully. So that's the major theme of today's presentation. So we'll kick off. I'll show you the agenda here. So the agenda for today's presentation is really just to give this overview of what the industry experts have suggested as the minimum level of key instrumentation required to monitor and keep your plant healthy and happy. We'll go through those. These are a little bit like these are the tools a good mechanic has in his toolbox: conductivity, cation conductivity, pH, and on. Then we're going to discuss some optional tools that are needed. And in fact, things like degassed cation conductivity, I think, has really evolved from something that was optional when this concept in this document that we will talk about was first developed, but is becoming more and more standard, just like silica as well. And then we will kind of transition into where are these tools used. Just like Barry indicated, there are some locations in the plant where these measurements are not being performed. The instrumentation is not in place, which is a lot like driving down the highway at 100 miles an hour with one hand over your eye. It's just not a good recipe for safety. And then, of course, some Q&A time at the end. So I'm moving on here to where does this concept come from? So much as I've indicated, there's far too many plants that are under instrumented. And when you're under instrumented, it's really easy to fall into that trap of repeat cycle chemistry that Barry has highlighted and has data to prove that is a very real scenario. But we also want to flip that around, look at the other side of the coin, and really impress on the importance of you got to have your eyes on the ball. You got to have good visibility of what's going on in your plant. And that requires online measurements for fast response, for more accurate response, to minimize corrosion and suppress deposits. Now, many years ago, and it's been updated a few times now, IOPS and the Power Cycle Chemistry Group, with representatives from 21 different countries, with ties and linkages to EPRI, VGB, ASME, ASTM, all got together. And again, not once, multiple times as this document has evolved. We've had representatives of boiler manufacturers, turbine manufacturers, water treatment specialists, analytics specialists, control system specialists. They've all had a part in developing this information. And what was developed is a technical guidance document that basically I will review today with some additional information, some updates, some trends, and from my personal experience. But this document is available. It's out on the IOPS website. Hopefully you're aware of it. If you're not aware of it, I would encourage you to go download that and take a look at it. kind of the concepts behind that document and really the concepts behind this minimum instrumentation we're going to touch on. First, you've got to clearly identify, you've got to pinpoint the water chemistry problem, the failure, and be able to anticipate what will follow if that water chemistry upset is not addressed. So you've got to have the right instrumentation in the right location to be able to do that. Secondarily, these minimum instrumentation locations and the tools should provide a more holistic view. There should be some backup in terms of where these are located, how they're monitored, so that if you see an excursion or event, the first thing that comes to your mind is, oh, I bet that sensor is bad, or I bet that analyzer is bad. We want to take that out of the equation because you have enough instrumentation. And again, we're talking about the base level, the lowest bar here, but that lowest bar needs to at least provide some validation of one reading with another reading to indicate, yes, truly, this is a serious contamination. Then the next element is trust. And this kind of goes hand in hand with this redundancy. You're much more likely to trust your online instrumentation if it is being backed up and supported by other measurements. Maybe a quick example of this, a very tangible example of this, is if you're seeing a low pH alarm alert with your pH electrode. Is that being backed up? Is that being verified by your calculated or derived pH as determined by conductivity? And then lastly, this should be alarmed, and these alarms should go to your control room or your DCS system. And as Barry indicated, there's many plants, I've seen them, he's seen them, where you might have some nice sensors, you might have some nice transmitters. Those transmitters might trigger an alarm, but when you really say, okay, this is an alarm, why isn't anybody taking action? Well, that alarm never went to the control room. No one had visibility of it. That's the fundamental gap here that we're also trying to fill. So that's kind of the background. That's the concept. Now, what are these key instruments that we're talking about? No surprises here. It's going to be conductivity. It's going to start with conductivity. Conductivity gives you simple, fast determination of the ionic load in the water. It gives you a rough assessment of the purity of the water. In some cases, when you're adding things like ammonia, amines, hydroxide to your boiler water, those additives are really going to drive the concentration of your conductivity. And really that's why you also use those in conjunction with cation conductivity. In some cases, you can actually sort of kind of calculate what the concentration is by some of those additives. In other cases, that's not possible. We'll talk about that a little bit later. But this is, this is like the basic screwdriver you need in your toolbox. But there's some issues around conductivity. It's great, it's simple, it's easy to use. It does require a little bit of maintenance. Some periodic calibration would be nice. I visited a plant recently where the conductivity sensors had been installed 10 years ago, and they had never once been taken out of the housing. No one calibrated them, no one inspected them, and I was surprised, but that happens sometimes. The important point here is temperature has a great impact on the accuracy of conductivity measurements. Sometimes that's overlooked, sometimes that's forgotten. There's also optimization of the temperature compensation, as indicated here by this small chart. When you know the measurement sample is dominated by ammonia, you want to optimize the temperature compensation for that. If you're measuring cation conductivity, so the sensor is immediately after the cation resin, then you want to optimize the temperature compensation for that. So a helpful tip, on a simple measurement in your toolbox. Next up, cation conductivity, also known as cation after, or conductivity after cation exchange, CASE, or acid conductivity. The key here is obviously the sample must go through a column of strongly acidic resin. That's going to remove a lot of the additives, primarily ammonia. It's going to highlight and give you an early heads up on things like cooling water problems, especially with seawater plants. It's going to give you an early heads up of contamination coming in from the makeup water stream. Typically used for condensate, feedwater, condensed steam, or if you're in a plant with volatile or caustic dosing, cation conductivity is very key. Some notes on this, and this is also often overlooked, is now the resin column itself is part of the measurement. So it's really important you use higher quality resin. That resin is well maintained and it's really replaced prior to exhaustion. Again, I've visited far too many plants when I ask them, oh yeah, I'm looking at the column, that really looks like that resin should have been replaced based on the color change. Oh, well, we just let that go until we see a spike of conductivity. That's a really poor way of measuring and monitoring and controlling that measurement. pH, again, basic tool, been around for a long time. It's critical. We make a lot of decisions on it. We feel either good about the operation of our plant or we get really concerned when our pH levels go low. But it's surprisingly difficult to manage this in power plants and power plant waters for reasons we'll talk about here in a minute. But obviously, we've got to keep the pH in the alkaline range. In all ferrous systems, all steel systems, that's generally in the 9 to 9.8 range. If it's mixed metallurgy, it's a little bit less. Again, ammonia and organic amines and phosphates are all being added to maintain these targets. Some things to keep in mind here, though, is you've got to use the right tool for the job. And that really means using pH measurement technology that is designed specifically for low conductivity, low ionic strength installation environments for water conditions. pH is measured throughout the plant, throughout many industries, but you do not want to use, say, a general purpose or poor quality, very cheap pH electrode in a very pure water environment. That's just a recipe for disaster. Just some other notes here is, again, the quality of the measurement technology really matters here. This is a critical measurement. It's an important measurement. You're making important decisions on it. You want a good quality tool to give you that good quality feedback, especially, and Barry indicated this in his presentation, especially if you're tending towards the lower end of your pH range. That's very dangerous if you have inaccuracy in your measurement technology. So quality of the tool matters. A little tip here about many vendors, many suppliers measure pure water pH, but they're very dependent on these bowls. Now, I'm not saying whether that's a good design or a bad design, but if your measurement is dependent on the electrodes being in those bowls, you need to be vigilant on the contamination buildup in those bowls. I've seen some of these bowls that are just filthy. They've not been cleaned. They've not been, and what happens is they collect deposits in there, which then influence the accuracy. Regular calibration is important. And for sure, whenever possible, wherever possible, back up a pH electrode with calculated or derived pH from conductivity. It's built into many transmitters. It's easy to set up. So I'd encourage you to do that. Many customers I visit don't even know that capability exists. And in some cases, it exists with their current technology. So turn it on if you have it, use it if you can. Dissolved oxygen. This is also something that some people are a little surprised on. They just assume that low level DO is good, but too low of level can be very dangerous, especially when reducing agents or oxygen scavengers are used. If you have low DO and you're using these oxygen scavengers, now you run a very high risk of flow accelerated corrosion and triggering increased iron transport. Of course, on the higher end of the range, now you run the risk of under deposit corrosion, which can and has in many cases led to large scale tube failures in HRSG, high pressure evaporators. So reliable DO measurement is really essential. Again, I've visited many plants, talked to many operators and say, dissolved oxygen, that's just advisory. Not important. It is important because it is going to drive and protect the health of your protective oxide layers. Now, historically, dissolved oxygen was managed using a technology that relied on membranes. It was called. Some of those sensors got kind of a bad reputation because they were maintenance intensive. They required frequent calibration. Membrane itself could be easily damaged during iron transport events. So that led to, I think, the belief in some plants that, oh, it was just too much trouble doing the maintenance on those sensors. There is newer technology available, totally different, no electrolyte, no membranes. It uses light and luminescence technology, gives you a faster measurement time, a faster reaction time. This technology will alert you to oxygen ingress, air ingress of serious problems more quickly, and it has far lower needs for maintenance. There was a plant in Brazil that transitioned to this newer technology of sensors. They saved 400 man hours of labor in the first year they made that transition. Now, keep in mind that these oxygen scavengers and organic breakdown products can influence the results. Now, just keep that in the back of your mind because sometimes where the sensor is placed relative to where the oxygen scavenger is being dosed can have an impact here. And then carefully look at all the sample fittings that are delivering the sample to the dissolved oxygen sensor. You don't want any of those loose. You don't want anything allowing air to come in and interfere with that reading. And you also don't want to create any sharp bends that might create some cavitation that would interfere with the measurement as well. Now, moving to another basic tool in the toolbox, sodium. So sodium is based on online sodium ion selective electrodes. These are really, in a sense, a highly modified pH electrode, but they're designed to be blind to all the other ions in the water system. How are they made blind? Well, you need to pre-treat the sample, typically with ammonia or DIPA, because you've got to blast up the pH of that incoming sample to eliminate any cross interferences to allow that sodium electrode to only read sodium. If you do that first part correct, then you're guaranteed some really good accuracy at very low levels of detection of sodium. Now, over time, just a safety tip, over time, especially some kind of lower quality, maybe cheaper sodium analyzers and sodium electrodes, we'll see a reduction in the sensitivity and accuracy if they were only exposed to very high purity water with very low sodium content. That triggers the need to do more frequent calibration and in some cases, etching of the electrodes. Again, what's the trend? The trend is more and more analyzers that include automatic calibration calibration and automatic sensor conditioning. This dramatically reduces the amount of labor involved in calibrating, maintaining, and cleaning these electrodes. So use the newer technology when it's available. Now, moving to phosphate. In the past, you could measure phosphate using something other than an analyzer. But when dosing phosphate, really a direct online measurement is really preferred. It's better. It simplifies the measurement. And particularly, you want to avoid this problem of phosphate hideout and phosphate return. Those risks of phosphate hideout are elevated as the pressure goes up, it's elevated as load changes and cycling come into play, and it's elevated at plants that are using anything other than trisodium phosphate at the 3-to-1 molar ratio. So strongly encourage everyone to do that. And it is possible to kind of derive phosphate from looking at pH, conductivity, cation. It's possible to do grab sampling, take those back to the laboratory. But again, grab sampling's typically not frequently enough, or it's not done, and can lead to you thinking your phosphate dosing is in the right range, and it's not. Again, one of the reasons some plants, and even this document that we're kind of leverage some of this knowledge from, in the past, phosphate analyzers had a bad reputation. They consumed a lot of reagents, they took a lot of maintenance, and they were never really all that accurate when compared to lab measurements. Again, there's a new generation of analyzers on the market that do a much better job reducing maintenance, reducing consumption. And I would encourage you to look at some of these new technologies, some of these new analyzers that make it much, much easier and more convenient and lower cost of ownership of measuring phosphate. Now, moving on to another basic but required key measurement, and that is ORP. This is a key measurement if you have a mixed metallurgy plant. If you've got copper alloys, you really should be using ORP. And as this little graphic indicates, as you see copper corrosion, you're going to see changes in the ORP. It's a method that indicates the health of and what's going on with the copper alloy corrosion. It can also help you monitor and control the oxygen scavenger dosing. Some tips here is you can get ORP sensors standalone. They only measure ORP. Or now what is most commonly used is what they call combo sensors. So you can measure both pH and ORP in the same sensor. That's often gives you more visibility. Again, it gives you more redundancy. It gives you that holistic view that we're trying to look for here. Gives you more measurement points of pH. But calibration of ORP is very important, and it's often done incorrectly. So really reach out to your vendor, read up on a proper ORP calibration if you're going to use this technology. And again, think about where the dosing of the scavenger is relative to where the sensor is. Oxygen scavengers are a moving chemical reaction within your system and even within the sample lines leading up to where your ORP sensor is. Place that sensor too close to the dosing location or too far away from that dosing location, you're going to get erroneous readings. So that was kind of the review of the basic tools: conductivity, cation conductivity, pH, DO, sodium phosphate, ORP. Now we're going to move to these optional others. Now, again, times and trends change. You might argue whether or not these should be considered key or not, but we will review these one at a time. So degassed cation conductivity, also known as degassed conductivity after cation exchange. This takes a step back. So cation conductivity has a relationship with weak acids, has a relationship and changes when carbonate is involved, when CO2 is involved, when you have water that is in storage during load changes or shutdowns, and now you've got this highly purified water in storage tanks, it's very, very typical, very, very common for that purified water to absorb CO2. So then during the startup phase, you have this problem where you're seeing elevated cation conductivity, but you have no way of really knowing what's the level of that cation conductivity that's being driven by the CO2 contribution. So that's why you need to remove the CO2 to get back to that lower, more true reading of cation conductivity. Now, typically that's removed either by a reboiler or an equilibration, a stripping process with a gas stream. Those are the typical methods of removing CO2. Again, this is typically used, and in fact, probably a standard tool in any plant that's frequently cycled or a fast start, because it does allow them to start faster with more confidence in the steam quality. So much like temperature needs to be considered for conductivity and cation conductivity, you want to keep in mind temperature management of your degas measurement. You don't want to damage the resin. You want to make sure you have temperatures that are within range for accurate reading. And if you're using a reboiler, you want to make sure that the vendor has some capability to make sure that the final degas cation measurement is not negatively influenced by higher temperature coming out of that reed. Now, silica, this is probably one that many people would argue should be a key measurement. There are typically targets set for silica in drum boilers. However, if you're talking to a turbine manufacturer, they're going to have targets like in their warranty conditions around the allowable amount of silica that they want or don't want to carry over into their steam turbine. The risk here is those silica deposits negatively impact the actual performance of the steam turbine and have an elevated risk of vibration because, of course, that silica has weight, and you add that weight over time, and it's never equally distributed. It's a lot like someone sneaking onto your car every night and placing a new lead weight on your wheel in a random location. Over time, you're definitely going to feel that vibration in your tires and wheels. The only reason that in the past this was considered optional, because there are some plants that have low levels of silica. It's consistently low level, either based on their source water or an excellent water treatment system, and they can get by with periodic grab sampling. So again, much like phosphate analyzers have had a little bit of a bad reputation in the past, some silica analyzers have had a bad reputation in the past. Again, high levels of reagent consumption, high maintenance requirements. Again, there's much better technology available that really has focused on reducing the cost of operation, reducing the consumption of reagents, reducing the maintenance, being easily able to measure from multiple streams, and even technology that allows customers to measure both silica and phosphate simultaneously in one analyzer. If you think about that, that gives you a very good ROI for measuring silica throughout the plant as well as measuring phosphate. So makes it much more convenient. Now, another optional tool, total organic carbon, really looking for organic contamination. That organic contamination has risks if your raw water has heavily organic in them, like you're pulling it out of a river or a lake or a stream that is heavily laden with organics. Now your water treatment system has to work harder, and those organics will impact your water treatment system. If you have a condensate polisher, organics either coming back from the condensate or in the other parts of the cycle will shorten the life of the resins there. But this is really an important measurement for those cogeneration plants, those sugar plants, those pulp and paper plants, those fertilizer plants, those refinery plants, where there's a very real risk that the production process itself may have a failure, and that failure may bring back organic contamination with the condensate. Really, the goal here is you want an online, real-time measurement of TOC so you can make a quick determination whether or not that condensate, that contaminated organic water is bad enough. You want to divert it. Maybe you want to send it to drain. Maybe you want to send it to a storage tank until you can solve the problem. But you need a sensor, and this is an example here where a TOC sensor, much like pH, conductivity, dissolved oxygen, can be used with a single transmitter, and you can now monitor 4 key contaminants or status of condensate return as part of that solution. So quick overview on the tools now, where to measure. This was something that Barry mentioned. This is a measurement that's typically missed, and this is on makeup water. So you need to verify that your makeup water treatment is not having a problem, and that problem is not introducing new contamination. So you need to measure conductivity upstream of that water mixing with your condensate. Then you would also want to use cation conductivity, especially if you have a storage tank, especially if that tank is open to atmosphere, if that's vented. You want to make sure, again, that cation conductivity is measured prior to the point of delivery of that water into the main circuit. You want to catch these kind of problems early. You don't want to see a problem later in the cycle and then wonder where that came from. You want to see where that came from. Again, this is a measurement point where you might have silica, and you would want to use silica here if the plant has some history of variability in the levels of silica, or if it's dependent on raw water that also has high levels of silica, and similarly to TOC and organic contamination. You should know the history and the risks of your plant relative to silica and organics at that measurement location. Now, moving on to condensate, highly recommended that you measure this after at the condensate extract pump discharge. This is going to give you the first warning of a condenser leak, first heads up if you've got regeneration chemicals interfering with your water here. If you've got contaminated condensate, again, the early warning should be helping you with this, but this is another chance for you to catch a problem and then verify with other sensors that you have a problem. It's going to give you a rapid alert to the corrosive ions. Sodium is a must for seawater cooled plants, even more so if you do not have condensate polishing. Again, dissolved oxygen, good must location here for detecting any air ingress. And then here's the optionals. The optionals are conductivity and pH. Again, part of this holistic view of what's going on. And then also optional degas here to confirm and to separate whether or not you're seeing an increase of cation conductivity that's being driven by CO2 in the water. Now, if you have a condensate polisher, that's great. Everybody should have a condensate polisher. It makes life so much easier. At the condensate polisher outlet, you should be measuring cation conductivity, sodium, and then as an optional traditional specific conductivity. Again, that's backing sodium. So,
2 minutes, Kirk,
okay.
please.
So then moving on to if you have feed water without a condensate polisher, again, you want to measure this downstream of your feed pumps. You're going to be looking at conductivity, conductivity after cation, so cation conductivity. You're going to be looking at pH. You're going to be looking at dissolved oxygen. So those become the key measurements if you're looking at feed water quality. Downstream of the feed pumps. Now, again, optional, if you have mixed metallurgy, if you have copper, this would be the location where you'd be wanting to measure ORP. Moving on to drum boiler. So really the recommendation is you should be taking these samples from the downcomer. So that's why I've used this illustration here. If you're running a boiler or an HRSG with no alkali, then the key measurements become conductivity, conductivity after cation exchange, and pH. And you can read here some of the reasons for that. Now, the optional, again, this is a location where you're going to be measuring silica. Now, it's sometimes very helpful. It's very nice to know how much silica is in the water because now you can correlate and you can verify whether or not you're seeing the expected carryover of silica from the boiler into the steam. Now, you can measure it here, but really the control level, more typically measuring silica in the steam. But again, with today's multi-stream sequencers, there's no reason why you can't do both. Measure silica in the boiler, measure it in the evaporator water, and measure it in the steam. Now, moving over to plants running on caustic treatment, very similar. Conductivity, cation conductivity, pH, and again, optional silica. With this notation that silica is less volatile in boilers with caustic dosing than AVT dosed. A little bit of a tip, something that's often overlooked, but it does change the volatility of silica and the rate in which it carries over into the steam and into the steam turbine. So again, measure it both, no reason why you can't. Now, if you've got a plant running on phosphate here, now you can measure conductivity, cation conductivity, pH. You know, now you're looking for multiple inputs on this multi-dimensional measurement challenge to really maintain the correct dosing levels of phosphate. You want to avoid this situation where I've got with my little graphic here where phosphate's up, phosphate's down, pH is up and down as it's being driven by the phosphate. You want to keep a steady eye on the ball. You want to keep steady control of the phosphate. And again, you can see here as I talk about pH, some of the risks of using only pH when you're dosing phosphate. So again, if you're running phosphate, sometimes it's just really necessary to have direct measurement, direct control of your dosing. You want to minimize that hideout. You want to minimize any risks of misinterpreting the other data. And in some cases now, sodium becomes an optional measurement, particularly if you're not using trisodium phosphate, particularly if you're not using the 3-to-1 molar ratio. Sodium becomes kind of transitions from an optional measurement to a strong advisory measurement there. And again, much like in the other examples, silica monitoring in the boiler is good as well. Now, moving towards the end here, one of the areas Barry indicated is missing analytics when it comes to measuring steam. So because of that, I just wanted to review what are we trying to prevent here? What are we protecting against? We're looking to prevent and catch and prevent excessive carryover. We're looking to catch a problem from a temporary a temporary spray. That, again, an often overlooked source of contamination. And then we're looking for concentration of silica that could form deposits on that steam. Now, to get a good reading, it's important that the extraction probes are designed and located to give you a really true representative sample for steam, especially when we're talking about saturated steam. But if you don't believe that this is important, video that will hopefully impress on you the consequences of poor steam management. Clearly, you never want your steam turbine to look at that. So let's talk about the measurement locations a little bit more. So there's two typical locations upstream of the superheaters. You need to get that saturated steam. That's important for the carryover measurements. Barry will emphasize that. And but you've got to have that sample location. You've got to know where it is. It can't be ignored, blocked, shut off, broken. And then secondarily, and really the preferred location for online monitoring is downstream of those superheaters. That's going to give you measurements of your superheated or your reheated measurement point. But that's the point where you're going to catch a problem with your attenuation spray. And it's important that you catch that early. I often say that you may have done a year, multi-years of good steam management that can be thrown away in a day by spraying really highly contaminated water into your steam turbine. So don't lose all that good effort with bad attenuation spray. Now, when we're talking about superheated and reheated steam, cation conductivity, sodium, and again, if either of those measurements are showing consistent, persistent high levels, this is a indication, a strong indication that your boiler drum has a problem or you've got really serious feedwater contamination. Both of those problems need rapid attention. And again, this is where you want to measure silica because you want to catch excessive silica carrying over into your steam turbine. This is even more important if you suspect you have non-reactive or colloidal silica. Again, that's often dependent on your source water. That often varies with the seasons, but you cannot control, you cannot manage what you don't measure. This is a good way of managing that much more successfully. And again, for fast startup or frequently cycled plants, this is the location that's most typically used for degassed activity. And that also gives you cation conductivity measurements, gives you pH measurements, and lets you validate some of those other measurements again for that more holistic. So that's it for my presentation.